So let's start. Okay, so as we said in the DNP experiment, we have three phases. One which is to polarize. So we'll talk about DNP mechanisms and how to do DNP on next week. Then how to transfer, melt and transfer without losing too much polarization, and then inject in the NMR spectrometer and measure the hyperpolarized signal with sufficient stability and repeatability for your application. So there are many polarizers that have been built so far. I will just review a few of them. The first one was the HyperSense. This was an Oxford Instrument device that was built under license of GE. They built, I don't know how many, maybe between 30 and 50 of them. I think 2 or 3 of them are still functional today. It operated at 1.5 Kelvin, 3.35 Tesla, where the electron polarization is more than 95%, 94 gigahertz frequency on small sample, 40 microliter. And it used to consume about 50 liters of liquid helium per week. Today, this is discontinued. There's no more service, so it's really hard to maintain this equipment, but some groups manage, like the Hilti group or the group of Lucio Friedman, but there are really, really few machines that are actually working. Then, more recently, GE released the SpinLab. It's a very sophisticated device that is really meant for clinical application for humans. So it's very expensive. It's about 2.5 million. And each time you polarize a sample, you need a dedicated sample container and a fluid pass that costs several thousands of euros. So this is a very expensive device that is okay for human application, but is not really meant for NMR or for preclinical imaging. Their polarizer operates at 5 Tesla, that's 100 gigahertz microwave frequency. They have 4 samples that can be polarized at the same time. It's cryo-free, it's sterile, but it's, as I said, costly. And even more recently, Bruker has embarked in the project of building a prototype polarizer, and that's the polarizer you're going to work on here. So we have this prototype polarizer at the CRMN. It's operating at 1.2 Kelvin, 7 Tesla. That's almost 200 gigahertz microwave. It has some nice features for frequency modulation, frequency gating. You can work on samples up to 250 microliter. It consumes a lot of helium, 100 liter per week. You can do cross polarization, you can change the probe, and there is now a cryo-free version that is in preparation. So this was the last prototype. There are only 3 prototypes like this, and the next version coming soon, hopefully next year, will be cryo-free and it will be a product. And it will not be aimed at clinical imaging. So it's only for NMR and for preclinical, for rats, mouse, etc., animals. There are actually more devices that have been built. For example, one in ETH by Michael Battel and Matthias Ernst. It's also a multi-sample. I don't know if it's still operational. They published that in 2012. One by Lloyd Lumata in US. There is one also built by Mathieu Baudin and colleagues in Paris. One that is here, built by us and with the help of Bruker, and many parts were built by Morgan Cellier, who was PhD in the team. One by Arnaud Comment, one by Jan Henrik, who has now turned into a startup called Polarize. So they sell the system. It's a DNP polarizer that is based on the cryo-free system by Cryogenics Limited. And they have sold a few, I think 10 or 15 machines like that. So yeah, there is a real need for equipment, because for now there's either you go for the HyperSense, which is discontinued, so you have to buy an old one that is not maintained, or you buy a SpinLab, which is super expensive, or you buy from one of these startup companies. And hopefully Bruker will come with a product that will be suitable for NMR spectroscopy soon. We have a question from Ekaterina. So the question was, what is used instead of helium? So it's helium, but it's a closed loop system. So in the cryo-free system, you have a cooler that liquefy helium, and then the helium is sent to the sample space and it's pumped and recirculated. Yeah. So all these devices, they're based on the same principle. You have a magnet, you have a cryostat that cools down your probe, and in the probe you have your sample in like here in blue that is next to a microwave waveguide that brings the microwave and shine the microwave on the sample. You have often an RF coil to pick up the NMR signal and to monitor the polarization buildup, or you can do more fancy experiment like the one we're going to do here, like the CP, the cross polarization. So first thing you have to try is to bring the microwaves at the sample. So for that, we use some cavities that are not real cavities. They're just boxes that are gold plated to reflect the microwave. Why? Because the wavelength of the microwave is very small. It's a millimeter, and the sample can be several millimeters. So you cannot really have a resonant structure. It's non-resonant. And this is just a video showing one version of our coil. So you see here quite complicated structure of several coils that can pick up the signal of carbon and proton. And you see here the microwave guide on the side. We'll see that in more detail during the training. So all this hardware will be reviewed on the Wednesday afternoon. So we'll talk about how the cryostat works. We'll show you the cryostat in operation. We'll show you the probe, how we tune the probe. We'll open the probe so you can see how it is built. And then we'll talk about the microwave with Quentin. So this will be all reviewed into detail on the Wednesday afternoon. Once you have this all this hardware, you can start to do DNP. So most of the people do DNP with trityl radical. So it's a carbon-centered narrow line radical. We'll talk about it later. And you directly shine microwave on the electron, and you transfer directly the polarization from the electron to the carbon-13. So that's what we call direct polarization. You can polarize carbon, you can polarize nitrogen, you can polarize phosphorus, any low gamma nuclear spins, but it's not very good to polarize proton spins for some reason that we will talk about later. It polarizes carbon up to, let's say, at 3 Tesla to about 20%. If you go to, if you add some gadolinium, so you can add some paramagnetic agent, you can boost the polarization and go up to 30, 40% in the best conditions on the best sample. And it takes quite a lot of time. You see here the time scale, it's thousands of seconds. So you typically need 2-3 hours to get to this high level of polarization. It's very long. That's why GE has a 4-sample device. So you polarize the samples, and during the day you dissolve the 4 samples, and that's it. So you do 4 samples per day, maximum, with the GE system. If you go up in field, like 6.7 Tesla, Capozzi and colleagues have shown that you can get really, really high polarization values, 60-70% carbon polarization, again, adding gadolinium. And this is all shown for pyruvic acid. It's a very, very special system that polarizes particularly well with trityl. And if you switch to mixtures, then it's becoming more complicated. But that's really the #1 radical that is used in the field. And that's not what we're going to show here. We're going to use a very widely available and cheap radical, which is Tempo or Tempol. It's a nitroxide radical that we're going to use. It's very cheap. You can buy it at Sigma. The problem is that the DNP performances are not very good. So at 6.7 Tesla, it takes an hour or so to get about 30-40% polarization on C13. So it's less performant than the trityl if you want to do direct polarization. Okay, it's a bit faster, but it's lower.
What is the reason between, what is the difference?
So the difference is, it really comes from the line shape of the radical. It has a line shape that is really optimal for carbon polarization. The width of the EPR spectrum is really good. Whereas the Tempo is much broader, and the width makes it a poor radical for carbon, but a very good radical for proton. And I mean, there are other reasons due to relaxation, but mainly it's the line shape of the radical. you see the trityl is very symmetric. So it has a very narrow line of about, I don't remember, 70 megahertz, which is very close to the frequency of the carbon. And for some reason that we will talk about today and tomorrow, this is very good. Whereas the tempo, the line width is like 500 megahertz or more. It's very, very broad. So it's a poor polarizing agent for carbon. I mean, poor to some extent. But what we discovered is that it's a super good radical for proton polarization. So you can get proton polarization in a few minutes. It takes usually 3 minutes, 4 minutes to build up on protons. And you get polarization that goes from 60% to 80, even 90%. So it's hard to quantify the proton polarization for many reasons, but we know we get really high polarization on proton. Here you see one of the first, I think it's the first dNP spectrum at 6.7 Tesla of proton. So this is the polarization. So 1 being 100% as a function of the microwave frequency. So you get a positive polarization of 70% and a negative one of 80, 90%. And the build-up time is about 2 to 3 minutes, depending on the conditions. So because we saw that tempo is so effective for protons, we decided not to go for trityl, mainly because it was expensive, and to do proton and then to implement cross-polarization at low temperature. So we do two tricks that we will describe in detail next week. We do frequency modulation. So here you see the EPR spectrum of Tempol at 6.7 Tesla. And instead of shining the microwave at only one frequency, we just rapidly modulate the frequency to shine microwave on the constructive parts of the spectrum that gives rise to the dNP. And we usually modulate a few tens of megahertz, sometimes 100 megahertz widths. And that makes all the electron constructively participate in the dNP process. That's one trick. And the other trick is cross-polarization. So instead of polarizing carbon directly, what we will do next week is polarize protons, look at the proton polarization, and then do a radiofrequency pulse to transfer polarization from proton to carbon. And this takes about 1 to 10 milliseconds to transfer. And what we do usually is we do it several times. So we accumulate polarization on carbon and we repolarize the protons, and that way we get really high polarization values. So what we will do next week is we will combine this modulation and proton polarization and CP, and instead of the red curve, which is carbon polarization as a function of time, you get the blue curve, which is carbon polarization as a function of time, and suddenly you do a CP, so you get more polarization after 2-3 minutes. And after a while, you do another CP, and so on, and that way you can accumulate the polarization on the carbon and get polarization. I mean, we get routinely we get more than 50% polarization in 10 minutes or so. So this is not in the spin lab or in the polarizer from Jannin or in the Oxford instrument. So but this will be in the Bruker system. And so this will be on the Thursday morning. We will do dNP with all these methods. Direct dNP first, and then in the afternoon CP with Quentin, and then process the data to quantify the polarization in the solid state. Then we will prepare the solution state NMR spectrometer with Chloé, and then talk about melting and transferring the sample. Again, if you have questions, please interrupt. So for the dissolution, the principle is the following. We have the sample sitting at the center of the cavity that is highly polarized after a few tens of minutes. And suddenly we put this stick, and the stick has two capillaries, one that will bring the hot water and the other one that will collect the hot water mixed with the hyperpolarized sample. Usually we heat up to 450 K, so it's superheated water at 10 bar or 12 bars, and then we blow the hot water on the sample, and we collect the hyperpolarized solution on the output of the polarizer. And so this will be described in more details this is, I think, the Friday morning with Charlotte. Then the last step, inject and measure after transfer. So you need to have a fast injection, and this will also be described by Charlotte. We have a system where the sample is sitting at the bottom of the polarizer. We have a capillary that goes out in a HPLC valve that collects the sample in a loop. And then we have a liquid pump that pushes the plug of liquid with liquid to an injector. And we transfer at speed of about 4 meters per second. So we can shoot the solution at several meters through other spectrometers. And after the injection, you see here the spectrum. For example, this is hyperpolarized acetate. You see the carbonyl, but you also see here the methyl. And you see also the glycerol in this case. And in this example, we plotted the line widths as a function of time, and you see that right after injection, there is some bubbles and injection, so the line width is only 3 Hertz. And then after a few seconds, it drops down below a Hertz, and you can really do high resolution NMR on the hyperpolarized molecules. And I think this is a typical experiment we're going to do with a standard of molecule such as acetate. So this will be for the Friday afternoon, then talk about losses of polarization and processing the data. And if everything goes well, which does not always go well, you can have many problems on the way. We should get polarization levels on the order of 50% in about 10 minutes, then dissolve, hopefully not lose everything, but lose maybe a few percent or 10 or 20% and end up with 30% polarization in the liquid state. And when we do that on and on, we usually can have variation of several percent. And if we have an internal reference, the relative variation can be down to 1% at best. And the transfer can be really fast. At 4 meters per second speed, it typically takes 1 to 2 seconds to transfer to the NMR spectrometer. So that's it for the introduction. I hope I gave you a good overview of the whole experiment. I hope you have many questions, more than you asked, and hopefully we can answer that questions later in the course. So we can have some time for questions before we switch to the theory. I can answer your questions, so please go on. Yes, Diana?
Like excited, like at the frequency of the free electron, for instance, gadolinium and stuff like this, and it should be universal, like for instance, for every nucleus. But here, according to what you say, is like there is a special radicals for a special nucleus.
Yes.
So I don't know if, for instance, gadolinium will not be like meant for all nuclei or things like this.
Yes, absolutely. So Diana said, I don't know if you can hear.
So she's saying that it's nuclear spin specific. So each nuclear spin will have a specific radical that can polarize. And yeah, so for example, as I said, trityl is efficient for carbon or for phosphorus, but not for protons. Tempo is better for protons. And there are many other radicals like that that have some specificity. So we will discuss that in detail. And gadolinium is not really used as a polarizing agent. It's not very efficient. It's used as an additional paramagnetic species that act on the polarizing agent relaxation time. So when you have trityl, you add gadolinium to improve the performance of trityl. It can also improve the performance of Tempol to some extent. We never observed any significant improvement, but there are papers that suggest that it can also help. Yes, Chloé.
That the be around the same as the normal frequency of the nucleus for it to be effective, or is it more complicated?
But in our conditions, we think we have a lot of thermal mixing going on. And for thermal mixing to take place, you need the line width of the EPR to be broader than the NMR frequency. And the broader it is, the less efficient it is. So ideally, you just want it to be slightly broader than the NMR frequency. And temple is not too bad because it's broader than the proton, but not so broad, not too much.
For Diana's question, that it depends a lot also on temperature and field. So what you know on the MAS DNP is not true at all in dissolution DNP conditions. It changes up really a lot.
Yeah. Yeah, that's true.
That's also why they are designing new radicals for MAS DNP for high field, because they realize that the amicable detectors are not so efficient at the highest field.
Yeah, absolutely. Yeah, the cross effect collapse for high field.
Hey, I have a quick question.
Yeah.
You measure 50% of polarization in liquid state?
Solid state, and in
solid state,
liquid state,
okay.
we usually measure less than that.
Yeah. Okay.
I don't know what's the record that we ever measured. 50? Yeah. So we go up to 60, I think, in the solid state, but 50 is more like the routine, and in the liquid state, it's between 0 and 50.
Okay. Thanks.
Yeah.
This ring is more complicated in the solution than in solution state than in MAS DNP.
Why it's more complicated to preserve the polarization. I would say to polarize is not so difficult, but then to transfer and preserve the polarization can be really difficult for some molecules or from some configurations of the lab. And we will talk about how to sustain this polarization and the losses of polarization at the end of the course, but it's a big, big problem. You have groups that have bought a polarizer and never managed to get polarization in the liquid state. And that's because of the magnetic field trajectory between the polarizer and the MRI machine. For example, if you cross zero field, you can have very, very strange things that happen. And you, of course, at low field, you have also paramagnetic relaxation that is enhanced. So you have many, many problems at low field that can destroy your polarization. That's why we're going to talk about how to sustain the field with a magnetic line, with solenoids. In our case, it was a big problem. When we arrived in this lab in Lyon, we realized that we could not get any polarization in the liquid state. And it took us a year to get polarization in the liquid state, or 3 maybe. It was really hard because all the magnets are ultra shielded, and so the field would drop below a microtesla and everything would be wiped out. So we had to build some coils and some magnetic Albach arrays, and it's really tricky.
I have another question about that. Between your polarizer and your NMR spectrometer, you have a magnetic tunnel
Yes.
of 1 Tesla, something like that?
Yeah.
Okay. And so you don't have any space without magnetic field between these two, between the polarizer and the NMR spectrometer?
Yes, there is a transition between the polarizer and the tunnel.
Yeah.
And then between the tunnel and the NMR magnet, and that's where it's tricky. That's where you have to find strategies to sustain the field with plates, magnetic plates, or solenoids. You will see we have a lot of
Okay, nice.
magnets hanging everywhere in the air.
So did you build solenoids for that?
Sorry?
Did you build some solenoids for that?
Yes, yeah, absolutely.
Okay, nice. Thanks.